Hi everyone. Through this class, I am going to discuss the basics of infinite impulse response filter. The filters designed by considering all the infinite samples of impulse response are called IIR or infinite impulse response filters. The specification of a digital filter will be desired frequency response HD of e raised to j omega. The desired impulse response HD of n of the digital filter can be obtained by taking inverse Fourier transform of HD of e raised to j omega. In digital domain, the processing of infinite samples of impulse response is practically not possible. Hence, direct design of IIR filter is not possible. Therefore, the IIR filters are designed via analog filters. In the design of IIR filter, the specification of an IIR filter is transformed into specification of an analog filter using transfer function h of s. Then the analog filter is transformed to digital filter with a transfer function h of z. The analog filter with the transfer function h of s is stable if all its poles lie in the left half of the S-plane. S-plane and the Z-plane, they are complex planes, and the S-plane is used to represent the continuous time systems, whereas Z-plane is used for discrete time system. In S-plane, here the axes are sigma and j omega. So any point in this S-plane, that is S1, which is equal to sigma 1 plus j omega 1. And in Z-plane, in this diagram, axes are represented by U-axis and V-axis. And here this V-axis is imaginary axis. So any point Z1 in this Z-plane, that is equal to U1 plus JV1. For the conversion technique to be effective, it should possess certain desirable properties. They are, first one, the imaginary axis in the S-plane should map into the unit circle in the Z-plane. Thus, there will be a direct relationship between two frequency variables in two domains. Second one, the left half of the S-plane should map into the interior of the unit circle in Z-plane. Thus, a stable analog filter will be converted into a stable digital filter. The designed transfer function of the filter should represent a stable and causal system. For stability and causality of analog filter, the analog transfer function should satisfy the following requirements. First one, the HA of S should be a rational function of S and the coefficient of S should be real. Second one, the poles should lie on the left half of the S-plane. Third one, the number of zeros should be less than or equal to number of poles. For stability and causality of digital filter, the digital transfer function should satisfy the following requirements. First one, the h of z should be a rational function of z and the coefficient of z should be real. Second one, the pole should lie inside the unit circle in z-plane. Third one, the number of zeros should be less than or equal to number of poles. Advantages of digital filters. The value of resistors, capacitors and inductors used in analog filters changes with temperature. Since digital filters do not have these components, they have high thermal stability. Second advantage is in digital filters, the precision of the filter depends on the length or size of the registers used to store the filter coefficients. Hence, by increasing the register bit length, The performance characteristics of the filter like accuracy, dynamic range, stability and frequency response tolerance can be enhanced. Third advantage is the digital filters are programmable. Hence, the filter coefficients can be changed at any time to implement adaptive features. Fourth advantage, a single filter can be used to process multiple signals by using the technique of multiplexing. Disadvantages of digital filters. First one, the bandwidth of the discrete signal is limited by the sampling frequency. The bandwidth of real discrete signal is half the sampling frequency. Second disadvantage is the performance of the digital filter depends on the hardware. That is, it depends upon bit length of the register in hardware. Important features of IIR filters. First one, the physically realizable IIR filters do not have linear phase. Second one, the IIR filter specifications include the desired characteristics for the magnitude response only. Comparison of digital and analog filters. Digital filters operates on digital samples of the signal, whereas analog operates on analog signals. Digital filter is governed by linear difference equation, whereas analog is governed by linear differential equation. Digital filter consists of adders, multipliers, and delay implemented in digital logic, whereas analog filter consists of electrical components like resistors, capacitors, and inductors. In digital filters, filter coefficients are designed to satisfy the desired frequency response, whereas in analog filter, the approximation problem is solved to satisfy the desired frequency response. Magnitude response of ideal analog low pass filter is like this. Here this is our pass band and this is stop band. We can see that the transition from pass band to stop band is sudden. But in practical case, the transition is gradual. And here the modulus of h of j omega is plotted with this omega. And we can see that passband edge frequency is noted as omega p and stop band edge frequency is taken as omega s. And the gain corresponding to this passband edge frequency that is noted as AP and stop band edge frequency gain is taken as AS. And this is for low pass filter, and for the high pass filter, the ideal magnitude response is like this. Here also we can see that there is a sudden transition from stop band to pass band. But in practical case, here also the transition is like this. It is gradual. And this is our stop band and this is our pass band. Pass band edge frequency it is noted as omega p and stop band edge frequency is taken as omega s. Magnitude response of ideal analog band pass filter is like this. And the magnitude response of practical analog band pass filter is like this. And the magnitude response of analog band stop filter is like this. And that of practical band stop filter is like this. For getting the magnitude response of ideal digital IIR low pass filter, we plot the values of modulus of HD of e raised to j omega versus omega. And here also we can see that this is our pass band and this is our stop band. And the cutoff frequency it is marked as omega c. And in practical case transition is not sudden. Here also we can see that it is gradual. So we have a pass band edge frequency omega p and stop band edge frequency omega s. And the gain at a pass band stop frequency that is AP and stop band edge frequency that is AS. And that of high pass filter is like this. This is stop band and this is pass band. Here also modulus of HD of e raised to j omega is plotted with omega. Practical case transition is gradual. Here we have a stop band edge frequency omega s and there is a pass band edge frequency omega p. Frequency response of ideal band pass digital IIR filter is like this and practical band pass digital IIR filter is like this. And the magnitude response of ideal band stop digital filter, it is like this, and practical digital IIR band stop filter is like this.